Good afternoon, dear students. Now the topic is torsional vibrations. So, what is mean by torsional vibrations? So, this is the third type of vibration. That is the third type of vibratory motion. That is when the particles of the disc or shaft moves in a circle about the axis of the shaft. The it is known as the torsional vibrations. So when the particles of the shaft moves in a circle about the axis of the shaft, it is known as the torsional vibration. So in this, the shaft is twisted and untwisted alternately. Okay. So and torsional shear stresses are also induced in the shaft. So that thing happened in our particular shaft. Okay, so that type of vibrations are calling as torsional vibrations. Twisting. Okay, when we are getting the some twisting of the shaft in a circular path, So that is known as the our torsional vibration. So now we are going to find out the natural frequency of free torsional vibrations. So in this, consider a shaft. Consider a shaft of the negligible mass whose one end is fixed and another end is the carrying a disc. So that is the diagram is also here. So let us take the one end is fixed and another end carrying the some mass. So when it is so what type of vibratory motion? It is the circle. So that means the twisting of the our particular shaft by the external by the our this mass by the mass. So this is the our torsional vibratory motion is there. And now before going to derive the our natural frequency, so let us know the some symbol notations. Let us know the notations. So that is the theta. Let theta equals to angular displacement of the shaft from mean position after time t seconds. After time t. And small m is the mass of the disk. And I is the mass moment of inertia of the disk. I is the mass moment of inertia of the disk. And k is the radius of gyration. And q is representing with torsional stiffness of the shaft. So now coming to the derivation part. So let us find the our restoring force. Restoring force. So that is the it is also similar. Okay, it is the procedure also similar to the in our natural frequency of longitudinal vibration. So, but the smallest amendment is have additional additional notations are there. Those are the representing with q and theta. Okay, the displacement is replacing with theta, angular displacement theta, and stiffness is replacing with the torsional stiffness q. So this is the restoring force value is the q theta here. But in our vibrations, longitudinal vibration, simply to write Sx. But here q theta. Okay. So now we are going to write this similarly to write the accelerating force. Accelerating force equals to I into d square theta by dt square. I into d square theta by dt square. So restoring force is considered as the equation number 1 and accelerating force is considered as the equation number 2. Now we equating the 1 and 2. So then the restoring force is opposite to the our accelerating force. So that is the minus, that is represented with minus. So I into d square theta by dt square equals to minus q theta. Actually minus q theta. So this equation is simplified with that. Okay. Right portion is taking into the in our left side. So then I into d square theta by dt square plus q theta equals to 0. So then it may also written as d square theta by dt square plus q by I into theta equals to 0. So let us take the equation number 3. So this equation is seems to be our basic fundamental equation of the simple harmonic motion. So that is the d square theta by dt square plus omega square ex equals to 0. So when we compare the both the equation, then omega equals to square root of q by I, square root of q by I. And when we know the our omega value, then simply to find the time period. Time period means 2 pi by omega, 2 pi by omega. And similarly to write natural frequency of torsional vibration, Fn equals to 1 by t suffix p equals to 1 by 2 1 by 2 pi into square root of q by I, square root of q by I. So in this, important thing is there. So actually, in our longitudinal vibrations, it may also have the the value has uh, s by m, but in this place, that is replacing with that q by I, q by I. So that means mass is replacing with mass moment of inertia, and stiffness notation is changing here. So that is the q. So that is the small amendment is there. And now, so for getting the q value, so let us take that this is the torsional stiffness equation. Let us take the torsional stiffness equation, that is the T by J equals to C theta by L. T by J equals to C theta by L. And similarly to write the T by theta equals to Cj by L. T by theta equals to Cj by L. And now here T by theta is also replacing with the Q stiffness. Okay, Q equals to Cj by L. So therefore here they may also represent that T by theta. T by theta equals to Q. Okay, torsion. So what is the torque is there? The torque value T by theta is also replacing with torsional stiffness Q. So therefore Q means Cj by L. So in this, the notations, just to have to rewind the notations. So already known these notations, that is the C equals to modulus of rigidity, and J equals to polar moment of inertia, and L is the length of the shaft. Okay. So polar moment of inertia formula is already known for shaft, that is the pi by 32 d power 4. Okay. If you want to find out the our natural frequency, first you have to find the torsional stiffness Q. So by the help of this formula, Cj by L formula. So that is very important. So have the problem, okay, regarding the earlier topic. So that is the a shaft of 100 diameter and 1 meter long has one, and 1 meter long has end one of its end fixed, and another end carries the disk of mass 500 kg at a radius of gyration 450 mm. The modulus of rigidity of the shaft material is 80 giganewton per meter square. Determine the frequency of free torsional vibration. So from the problem description, you have to write given values. So D equals to 0.1 meter and L equals to 1 meter, and mass is the 500 kg and K is the 0.45 meters, and C equals to 80 into 10 power 9 Newton per meter square. So in this, first we have to find the our polar moment of inertia for getting the Q. So that is the polar moment of inertia of the shaft. J equals to pi by 32 into d power 4. So just substituted the d value, then to get the our polar moment of inertia. That is 9.82 into 10 power minus 6 meter power 4. So now going to take the our torsional stiffness. So that is the Q equals to Cj by L. So C already know 80 into 10 power 9, and J is the 9.8 into 10 power minus 6, and L is the 1. So just make the calculation. So then the value has to arrive 785.6 into 10 cube Newton meter. So that is the our stiffness, torsional stiffness. And now going to find the our moment of inertia of the shaft. So I equals to mk square. I equals to mk square. M is the 500 and k is the 0.45 square. Just substituted the values and make the calculation. So then the value is 101.25 kg meter square. So Q is known and I is known. Then simply to substitute the in our main equation. That is the frequency of torsional vibration. F suffix n equals to 1 by 2 pi into square root of Q by I. So that equals to substituted the q value and I value in our equation. Okay, just you have to make the simple calculation and get the value. So that is the 14 hs. How much? 14 hs is the our torsional vibration value. 14 hs. Next topic, effect of inertia of the constraint on the torsional vibration. That means in earlier case, we are negligible the mass of the shaft, but now they are also consider the shaft of the mass. So that may also consider, okay, that may also calling as constraint. Consider a constraint. Consider a constraint. That means shaft mass is also considered here. So in this same situation, okay, condition will be the same. One end is fixed and another end is carrying with some mass, okay, mass of the disc. And in this, you have to take the one small element, one small element. Okay, so small element is there. The small element is having some distance from the fixed end, that is the x, and their width is the delta x. Width is the delta x. Now, before going to start the derivation part, let us know the some symbol notations. In this, omega is the angular velocity and m is the mass of the constraint, small m. Small m is the mass of the constraint and L is the length of the constraint. So MC, M suffix C is the total mass of the constraint, total mass of the constraint, ML. And K is the radius of gyration and I suffix C is the total mass moment of inertia of the constraint. So for getting the total mass moment of inertia, that is ck square, m suffix. Now consider a small element at a distance x from fixed end. Consider a small element at a distance x from the small end x at a distance x from the fixed end and the length of delta x. Therefore, have to take the our moment of inertia. Have to take the moment of inertia of the element. So moment of inertia, okay, equals to m into delta x into k square. M into delta x into k square. So that equals to delta x by L into mk square L. So that means dividend with the our L. Dividend with the dividing and multiplying with the L here in this place. So when we are dividing and multiplying with the L, so then the equation has to change it here. So that is the delta x by L into I suffix c. I suffix c means ML case. So that it has been arrived here. Okay. So delta x by L into I suffix c. So that is the moment of inertia of the small element. Small element. So now, similarly, to find the angular velocity of the element. Angular velocity of the element. Element angular velocity. So that equals to omega by L into x. Omega by L into x. So just compare the the velocities. When we compare the both the velocities, they may also have to write here. So that is the our omega by L into x. So that is the at the the small element are having the velocity of omega omega small omega into small omega and their distance is x and velocity of the mass of the disk, angular velocity of the mass, angular velocity of the mass of the disk is omega into the omega and their distance is L. So when we compare that, so that is the omega by L, uh, small omega by x equals to small omega, okay, small omega by x equals to omega by L. So when we compare both the velocities, so then small omega equals to omega by L into x. So that is the our angular velocity of the element. So now we have to take the kinetic energy possessed by the element. So what is the formula for kinetic energy? Half into I omega square. Okay, half into I omega square for shaft, half into I omega square. In this, half into I means delta x by L into IC, and omega means omega by L into x square. So just simplify the equation. I suffix c into omega square x square y. This is the kinetic energy for small element. Kinetic energy for small element. Now going to find the total kinetic energy of the constraint for shaft. For getting the shaft kinetic energy, just let us take the integral of the our earlier equation with the limits of 0 to L. Integration of IC omega square by 2L cube into x square dx. So just what is the constant term is there? IC omega square by 2L cube taken out from the integration. So then the x square dx is the integral of x square dx is x cube by 3. Limits are 0 to L. So then IC omega square by 2L cube. IC omega square by 2L cube. Sorry, IC omega square by L cube is written as IC omega square by 2L cube into L cube by 3. So when we apply the our limits, so then L cube cancellating here. So then the term is okay, written as 1 by 2 into IC by 3 into omega square. That means it seems to be again kinetic energy of the equation. So in this IC is replacing with I is replacing with IC by 3. So uh, when we consider the shaft mass or mass of the shaft, so then additionally to add it with the value of IC by 3 in our formula. So that's why Fn equals to, okay, natural frequency of free torsional vibration, Fn equals to, actually we are missing some terms. So that is the 1 by 2 pi into square root of q by I plus IC by 3. Q plus IC by 3. So that is the small difference is there when we consider the shaft mass and when we neglect the shaft mass. Okay, so this is the effect of constraint for torsional vibrations. For torsional vibration. Do you understand? So it is also similar pattern has followed. Okay, similar pattern has followed these derivations also. So what we have done in our earlier sessions, so that is the our longitudinal vibration and transverse vibrations. Uh, Again, we are also repeating the same procedure. Just observe the formula for effect of constraint for free torsional vibration. So that is the so that is 1 by 2 pi into square root of q by I plus I1 by IC by 3. So here that is also replacing, okay, IC is also written as I1 also here in our notes point of view. So whatever it may be, the notation is there, IC by 3. Now, next topic, free torsional vibrations of a single rotor system. So just all of you observe that. So the diagram, so simple diagram is there for single rotor system. So it is also similar to the in our earlier diagram. So that is the shaft is fixed at one end, and another end is carrying the some mass of the disc. But the other end is carrying, okay, the other end is arranging with the one rotor, arranging of the one rotor. So when we arranging of the one rotor, okay, so then the rotor is also given to the some motion, okay, some motion. So that motion means it may also give the twisting of the shaft. So then when we arranging the our rotor of the other end, so then you have to find out the natural frequency. So then it is also similar, just all of you have to that. Therefore natural frequency for free torsional vibration for a single rotor system, for a single rotor system, for a single rotor system, Fn equals to 1 by 2 pi into square root of q by I, square root of q by I. So whether we arranged the one mass of the disk or whether you are arranging a one rotor, whatever it may be, so that natural frequency value will be the same. So that is the 1 by 2 pi into square root of q by I. Now, in this, they may also said that amplitude values, that is that the amplitude of vibration is maximum at the free end where single rotor is attached. Okay, so that is definitely happen. So amplitude of vibration is maximum at the free end. Okay, maximum, and zero at fixed end. This section of the shaft where amplitude is zero is known as a node. The section of the shaft where amplitude is zero is known as node. Where we are having the zero amplitude on a shaft, okay, on a section. So that is known as the node. Okay, that portion have to put it the one node. So that is the node. That is known as the node. Now going to take the second one. So that is the our free torsional vibrations of two rotor system. Two rotor system. Just observe that two rotor system. In this two rotor system, let us take the shaft, and the shaft both ends are arranging of the rotors. Both ends. One, okay, both ends are arranged with the rotors. That is the A rotor is there and B rotor is there, and both are trying to twist the total shaft. Both rotors are trying to twist the shaft. So then you may also find out the natural frequency of the shaft. So now have to write our natural frequency of torsional vibration, free torsional vibration formula. So that is the at the rotor A, at the rotor A, F suffix Na is the 1 by 2 pi into square root of Cj by LAIA. So that means QE is replacing with Cj by L. QE is replacing with Cj by L. There is no difference between the, okay, this one too and earlier. Cj by L. QE is replacing with Cj by L. So that is the Cj by LAIA. So let us take the equation number 1. And similarly to write f suffix nb equals to 1 by 2 pi into square root of cj by lb ib. So why we written as the our la and lb? Why? Because when the rotors are trying to twist the shaft, then okay, we may also get that, okay, the amplitude value. So their amplitude values at the one section, at the one section going to zero. At the section, at the one section is going to zero. This place that, okay, where the amplitude is going to where the amplitude value has to zero, that place is that place has to form one node. So that is the node is there. Node is representing with n. So now A rotor is there and B rotor is there, and their amplitude values. Okay, so that is the our P to Q, P to Q. So now these are the these are the their amplitudes. The amplitude values are okay, and their amplitude height value is the small a and small a is there, and their length to the from rotor A to node length is the LA, and rotor B to node position length B. Okay, sorry, LB. So that's why we consider as the our LA and LB at the rotor A and rotor B. So therefore, rotor A natural frequency at the rotor A equals to natural frequency of rotor B. Both are equal. Just equating the both the frequencies. So when we are equating that, their formulas 1 by 2 pi into square root of Cj by La Ia equals to 1 by 2 pi into square root of Cj by Lb Ib. So in this, common terms are cancelled. So then the remaining terms are LAIA equals to LBIB. LAIA equals to LBIB. So therefore, LA equals to IB by IA into LB. IB by IA into LB. So L is representing with the total length of L equals to total length equals to LA plus LB. So they have written one relation between the L suffix A to L suffix B. L suffix A to L suffix B. Those two are not rotating in same direction. Both are opposite direction. So here someone raised the doubt. Those two rotors are rotating with same direction. That is okay. Those two are rotating. Okay, A rotor is rotating with clockwise direction and B rotor is rotating with the anti-clockwise. So how many rotors has taken? So those all are followed with one is clockwise and another one is anti-clockwise direction. That is important. Okay, good doubt. Number 47. Now we have written relation between the LA and LB. So that is the LA equals to IB by IA into L suffix B. Now going to take the third one. So that is the third case. Free torsional vibrations of three rotor system. When we arrange three rotors of the shaft, so then again we may also calculated our frequencies and their relations between lengths between the lengths. So that is the when we arranging the three rotors of the system. So then uh, the shaft has two ends, both ends, the shaft both ends are there. So A rotor is one end and mid of the session is B rotor, and at the end of the shaft is the C rotor. So and if you are observing that A and B, both are going to opposite directions. So that is the A is clockwise and B is the anti-clockwise, and B is anti-clockwise and C is clockwise. If B is rotating anti-clockwise, then C is rotating clockwise. So that way you have to arrange so the rotor. And now when we are arranging that, the distance between the our A to B, L1, and B to C is L2. So now we are going to find out the amplitudes and their nodes. So why? Because when the rotor A and B are rotating with the opposite directions, so then those are forming a one node. Those are forming with those have to form one node N1, and B and C. B and C, those two are also forming one node. So that is the N1 and N2. Two nodes are there, and their amplitude levels are this type. Okay, so that amplitude graph has been represented here. So that is the this type of graph has been achieved here. So now when we get that nodes n1 and n2, then distance from the our n1 from the rotor A LA and distance from the n2 from rotor C is LC, and remaining distance is just written that L1 minus LA and L2 minus LC. Why? Because earlier already represented that L1 distance from the A to B and L2 distance from B to C. So this is the distances getting by the our nodes formation, after the nodes formation. Okay, do you understand that? So now going to write the our frequencies. So that is the FNA equals to 1 by 2 pi into square root of Cj by LAIA. Let us take the equation number 1. And FNC equals to 1 by 2 pi into square root of Cj by LCIC. So that is the FNC and FNA. Okay, easy to write here. Easily to write here. Now FNB equals to 1 by 2 pi into square root of Cj by IB into, okay, IB into 1 by L1 minus LA plus 1 by L2 minus LC. Okay, so this is the length. The length is there from node 1 to node 2. The distances has been represented from node 1 position to node 2 position from the rotors, from the rotor. This is the equation number. Now, so equating the 1 and 2, since the frequencies are equal. So why? Because those three rotors are arranging on a same shaft. That's why those frequencies are going to take equal. So that is the FNA equals to FNB. Sorry, FNB that equals to FNC. So now we are equating the 1 and 2. When you are equating that, so 1 by 2 pi into square root of Cj by LAIA equals to 1 by 2 pi into square root of Cj by LCIC. So in this common terms are cancellating here. So then the remaining terms are LAIA equals to LCIC. So LA equals to IC by IA into LC. IC by IA into LC. So that is the one relation has to achieve. Now going to take the our equating 2 and 3. So when we are equating 2 and 3, so that is the 1 by 2 pi into square root of Cj by LCIC equals to 1 by 2 pi into square root of Cj by IB into 1 by L1 minus LA plus 1 by L2 minus LC. So common terms are neglecting here, cancellating here. Then the remaining portion is 1 by LCIC equals to 1 by IB into 1 by L1 minus LA plus 1 by L2 minus LC. So why we are writing as the this relation? Why? Because so the nodes, when we are achieving the nodes, then the distances is very important. The distances from the rotor, okay, their distances from the rotor values are very important. So that's why uh, for simply to find out their distances by the help of their these relations, okay. So they may also give some cases. So that is the A and B rotate in the same direction and C rotates in opposite direction. So here you will you have to observe this thing. A and B rotate in the same direction and C rotates in opposite direction. So then what will happen? So then a single node is obtained between the B and C. So actually we have two nodes in our in our derivation, but okay, two rotors are in the same direction, then we may also get only one node. So when we get the only one node, so then amplitude values and their lengths are varying here. So their amplitude values and lengths are varying. So those amplitude values are written here. So that is the A1 by LA equals to A2 by LA minus L1 and A3 by LC equals to A2 by LC minus L2.